Is Zach
Yeah, Zach is most definitely here.
stalling? Oh, he's actually in the room. Yes.
I wasn't actually ready yet, but whatever, it's fine.
Wait, can you raid people who aren't online?
Apparently.
Wild. Okay.
Okay, so Zach, Stucky, we are alive.
I can see that.
Apologies. Hi everybody. My name is Obi-Wan Piz. This is Ensimplex Pachinko. Apologies for that. I was not quite ready yet. But thank you, Zach, for the raid. We are. This is gonna automatically start ads, isn't it? Ooh, okay, hang on. Well, how is everybody tonight? We are. There we go. We're going to be doing differential equations. Yeah, that says after hours. Whoops, I panicked. Okay, so new plan. Let me change the Femvox. Thank you very much. You know, that's another issue that I need to work out. Category math, because goodness knows. There we go. All right, we're actually in. Okay. This is gonna automatically start an ad on me, so you're. I'm going to refill my water and say goodnight to my family. So I will be right back, and I'm gonna also mute the audio on Discord so that y'all can get in if you're coming in. Thank you very much. I'll be right back. I promise. I'm sorry. Oh my goodness. All right, sorry everybody. Whee! Nice, Enigma. Thank you very much for running that poll. Yeah. No, Pen, it's fine. You didn't have to worry about snoozing. That is perfectly acceptable. um, yeah, no, there has not been a Twisters or even a Twister 2. This is the first time that they have decided to make a sequel for that particular franchise. Uh, which, okay. I have no real opinion. Um, works for me, I guess. Okay, so we're going to get into class here, and I'm going to actually unmute myself from Discord. Okay, so we are now live, and yay! We now have 2 persons in the speakers area with me. My name is Obi-Wan Pez. This is Nsimplex Pachinko. If you have not been here before, welcome very much. And if either of my co-hosts slash students would like to introduce themselves, Stucky, you want to go first?
Yeah, sure. Um, I'm Ian Stuckey. I go by uh, he, they, and I stream over on Ian Stuckey on Twitch. Just here to hang out. Heard there was some differential equations happening. It looks like some of the stuff uh, in the back half of the curriculum is new to me, as well as some scattered topics earlier. So I figured I'd see your take on it.
Alrighty. And Zach.
Hi, I'm Zach. I stream over Eat the 2i Pie, and we're having. I'm excited because DEs are my are things I love, and I'm interested in your take on it. As Stuckey was saying, I'm interested to see how this goes. I'm excited just how you run it too, because I'm learning different ways of doing stuff.
Yeah. Well, and it's going to be a mixed bag, I'm sure, as I start going through the curriculum, because there's a bunch of stuff that like, I've never taught it except in like in person in a classroom or online in a very nope, okay, sorry, something blinked at me. Oh, there it is. Oop, oop. We have more people coming in. One sec. Oops, what did I just do? Oh.
Yeah, so I'm gonna talk to Phoba's question in the chat. The For me, in the elements, the servers, the channels where this class is being hosted were hidden. So if you go up to the top near the events uh, of the sidebar in the elements, you can find a thing that says channels and roles, and that will allow you to look at the full channel list and find the ones for this course if they're not already given to you.
Okay. And we had a couple of people drop into the event stage audience. If you are intending to come into class, I'm going to invite you to speak. If you don't want to do that and you were just intending to drop into the audience, that's perfectly fine too. I don't know how any of this works, so this is the first time that I have ever touched the event stage category here, so. All right. So yeah, this is kind of the first time that I've taught this not at my particular community college, and so things are going to be very different compared to how they were before, or how they were at my Okay, that is not what I meant to do. Sorry. Okay, live correct. Yeah, there we go. All right. Let's copy that. And we're going to drop this in chat here. As soon as I figure out where it is. There we go. Yep, I gotcha. Okay. Yep, thanks for dropping those in. Woo! Yeah, I was amused that the cursor had been left in Chaos Goblin mode. So when I actually started a session during my practice time, the cursor did not say Obi-Wan Pez. It said Don Dos Maths or something like that, because all of us had affected our cursor names to be a variant of Don Does Math. Anyway. Okay, welcome to Differential Equations, everybody. So my name is Obi-Wan Pez, as I've said before, and we're going to jump in to sort of an overview of differential equations first, naturally, and talk a bit about the history thereof and where all of these ideas kind of came from. So I gave a little bit of an outline here. I do have some other notes that I do refer to. Okay, so I'm sure that a lot of people have heard the story of the invention of the calculus. Would anyone like to give a synopsis? If you know the story. If not, I'll just go.
I want to hear you tell it.
Okay. That's what I used to tell my teachers all the time. Okay, so, once upon a time, a long time ago, roughly speaking, we're talking in the 1600s, we had a number of problems that were kind of key in mathematics in general. So, biggest amongst them being the brachistochrone problem, which I have under number 2 here. And bedtime story, nice. Basically, this was the concept of trying to get an object from point A to point B in the most rapid way possible using an arbitrary A and B point in the plane. So if we just have an object, how can we fastest way get something from point A to point B? And so it was judged to be an impossible problem to figure out, at least for a long time. People had devised all sorts of means for that to happen, made rails, basically took gutters and tried to shape them into the appropriate shapes. And, people came up with good ideas, but there wasn't really a settled answer in terms of, like, how can we make this 100% know what we're going to, 100% know what the correct solution is going to be. There was also Sir Edmund Halley, yes, that Halley, of Halley's Comet fame, who was trying to figure out the orbital dynamics of his particular comet that he was looking at. So the one that we see every 78-ish years, whatever it is. This is look-upable. I just haven't done it. Apologies. And he was trying to figure out the full orbital mechanics. How can we get a function that a function in time to show where this comet is going to be at any moment in time in our, again, they were simplifying this to 2 dimensions at first, and then we could expand beyond that. And the solution on that front first came from Sir Isaac Newton, who was a decent scholar. He had a bit of a problem, though, and that was that he was rather bothered by his advisor, Robert Hooke. Robert Hooke had a tendency of, let's just say stealing his students' work and then passing it off as his own. Not that he didn't do any of the work himself. It's possible that he did, in fact, contribute some, but nonetheless, because he was the superior and because he was the tenured professor, he just decided that, yes, well, this is my work because my students did it, and I oversaw them and or whatever else. Feel like Edison? So Newton had a few fallings out with him and decided to continually keep his work 100% private, away from everything else, and never have it show the light or see the light of day, mostly because he didn't want Robert Hooke taking credit for it. He would oftentimes have massive stacks of paper in his office. Think like, one of these shelves just turned sideways and multiple stacks. And whenever somebody asked him, oh, hey, do you have an idea how I might be able to improve this particular thing? He oftentimes would just go, yes, and pull out a paper and be like, I wrote about this 5 years ago. Now, these are apocryphal stories, but oftentimes building this human element within mathematics is something that a lot of us teachers like to do. The more stories we can tell about stuff, even if it's not maybe 100% true, as long as we're, either one, trying to look up the historicity of these things, or two, putting a big giant disclaimer on it, then, that'll be okay. So anyway, most of these stories are probably apocryphal, but at the same time, elements of truth exist. So one day, Edmund Halley came to Newton's office and asked him, do you have any ideas about this comet problem that I have? I'm trying to work out the full orbital mechanics. And Newton said, yes, in fact, and pulled out, again, another paper that he had that described something that might be useful. He didn't exactly have a name for it or anything like that at the time, but when Halley studied it and came back to Newton and said, you should really publish this, he said, no, I don't publish my work, you know that. And he said, no, you need to get this out to the broader populace. Like, everybody needs to know this. So Newton developed what became Principia Mathematica, his biggest work, and the one that fully outlines his ideas for what he called the calculus. And I am not just being an old person here, putting the in front of everything. No. It was also, let's see, the calculus is also a hint as to what's to come inside of Principia Mathematica, and therefore the calculus as a whole. Calculus is also a name for the pebble, or translation for the pebble in Latin. Virtually all of Newton's work was for differential calculus, So finding derivatives and ascribing meaning to differentials. So the way we know it now, what are differentials? If you don't believe it, you can look it up on Google. Yes, the Google. Thank you, Don. Yeah, 76 years. Thank you. Yes. Thank you, Phobos. Yep. So any differential is just this concept that we have been using since Newton's time, which we will usually call dx. It also has many different forms. So in Newton's time, often what he did was he wrote x with a dot above it to determine that this is the derivative of this particular variable. So x dot is the derivative of x. We would now say dx, but that's a story for 30 seconds ahead of time. So Newton's notation oftentimes uses this dot that goes above, and if he wanted a second derivative, then he would put two dots, and beyond that, he didn't really see much of a need to go beyond two dots or two derivatives. Third derivative, fourth derivative, fifth derivative, these were all theoretical. It didn't really mean a whole lot to him in terms of what he saw. These days, we also say that our, derivatives is going to be related to the phrase rate of change. And so if we're talking about x as position, everybody already knows what's first derivative of position. I guess you can also write it in if you're interested. Newtonian derivative notation is based. Any takers?
Sorry, I don't remember. I was trying to figure out when to participate and when not to. So can you give me the question again?
Yep.
I'm never sure. So
So if x is the function that determines position of an object, what is our first derivative of the position?
well, so the first derivative is going to be the rate of change of position. So if I change the position over time, that's the net measure of velocity. Yes.
Yep. Or 8
And then
also, type that out in chat.
Yeah. And then you can do the same thing with velocity and say, well, what's my change in velocity over time? And if I divide the velocity over time, that's going to give me my acceleration, right?
Yeah. So with Newton, this was pretty much it. He had your original function position, your velocity x dot, and the acceleration x double dot. He might have gone a third derivative just to talk about the rate of change of acceleration, but I don't think he had a name for it at the time. These days, and I'll actually just go like this. We'll make a separate table on the other side here, and we'll do the other notation in just a minute. Yeah, so Newton, for his part, also then said, okay, if we've got differential calculus, we've got x double dot is equal to 3 meters per second squared. Oh, that's heresy. It'd probably be feet. For Newton, anyway. Yeah. So if it was 3 feet per second squared, then Newton would have been able to figure out that, well, x dot would have come from a function that looks like what? Roughly speaking. Well, we're doing 3 feet per second squared.
So that's like a 3 times the how long has passed?
Right, and I didn't explicitly mention it, but yeah, definitely time is going to be our independent variable for this one. So we'll go with 3t. We're not going to use x, again, just because x in this case is position, so our acceleration isn't based on position, it's based on time. And Enigma is correct, yep. We're going to have some unknown factor. Anybody who's taken Calc 2, right, no, even Calc 1, you know that this is true, right? We need that plus c at the end, otherwise you get marked -1. So, and then we could go one more and say, okay, if that's our velocity function, what is our position function? So this is going to be x equals.
So what is it? You're going to take 3/2 t squared plus ct. I don't know how you want to notate this, but like a d maybe.
Sure. Continue the pattern, right? So we could either do subscripts or just different letters, but in this particular case, right, we can't combine our arbitrary constants because one of them is attached to now a linear function, whereas one of them is attached to nothing. It's just a constant.
So in other words, if the rate of change is 3, or like the rate of change, so then I need to find a function that represents the, antiderivative, and that's going to be a linear function.
Yep.
So that the constant function turns linear, and then a linear function, if I think about what function's rate of change is linear, that's a quadratic function or a parabola.
Yep.
Right?
So oftentimes the initial differential equations were solved by just kind of thinking about it. So, like, we know how to take derivatives of literally any function we come across. And then the question is, are we then able to flip this around and say, can we go this way to be able to solve what the function is that this particular derivative came from? So in this case, it's nice and easy. It's just polynomial functions all the way down in either direction. Basis of calculus is doing that with a really small change of position. Yes, yeah. So Newton's original idea started with taking just a function that's out in space and saying, all right, I want to know how to find the, there we go. Oop, no. I want to know how to find the slope of a curve. And a lot of people were saying, well, you can't find a slope of a curve. That doesn't make any sense. And he said, okay, fine. We'll find the slope of the line that is first a secant to this particular function. And hit the wrong button. Right, and then we'll find the next point somewhere along here. Oops, man, this is fine. And then we'll try to find points that are closer and closer and closer to our anchored point. So we're going to keep this point exactly where it is. We'll call it f comma f at x. And this point out here, there's a number of different ways we could call it. It could be just like x1 f at x1. It could be x1 y1. It could be, my favorite usually is x plus h, at least in this context, and f at x plus h. So in this particular notation, what we're doing is we're saying, okay, we've got a difference in our x and y directions. And Don, thank you for pointing this out, right? Oops, now we're good. Right, this is our distance h here. And then this is going to be our distance. This is f at x plus h minus f at x. That's a terrible thing to do, sorry. And so Newton's formulation for this was that our f dot was going to be the function where here we take these points and we start pushing them together, get ever closer and closer, so that our approximations for the slope first try. Yeah, not that one. Okay. And then we'll do this one in that color, just to say this is what we're trying to approximate here. So that one is going to be our ultimate tangent line. So the tangent line is going to occur when it's essentially the 2 points that we're connecting. The 2 points we're connecting are now actually on top of each other. Now, literally, we can't do that. Any Calc 1 student will tell you, okay, if you end up doing that, then you end up with a 0 divided by 0. It's an indeterminate form. That's pretty nasty. We don't like it. So we got a limit as h goes to 0 of that particular setup. All right. Okay. So in terms of what Newton was thinking, you know, we're going to be able to take derivatives of any particular function. We can work it out and try to find the best way. The delta x one? Welcome in, Dr. Gold. Right, and if we're being honest here, it probably is more likely that Newton had deltas in his in his stuff. And Dr. Gold and I approve of this definition. So anyway, once we simplify it down, this is just getting rid of the one piece at the bottom there. Had an x and a minus x, so that's gone. Alrighty, cool. All right, and then out of the wilds of Germany, Newton gets this letter which says, "Hey, so I'm very interested if you would at all have any enlightening ideas to put on this. I have discovered this rather interesting relationship that exists, and I'm wondering if you have any insight as to what might be able to work." And this person, uh, Wilhelm Gottfried von Leibniz, um, no, Gottfried Wilhelm von Leibniz sends a letter to Newton in England and says, your reputation precedes you, and I was wondering if you had any insight as to this. And he outlined a very similar process to the calculus. And Newton said, "Oh, well, I mean, yes, I've done something like this." And Leibniz, who was a school teacher, sent back essentially a reply that said, "I haven't seen any literature on it. Have you published it anywhere?" And Newton said, "Well, no. I don't publish my papers." And Leibniz then published in Germany. And Newton didn't really think anything of it. Nothing happened really for a few years. Eventually, again, Halley convinced Newton that he should publish Principia. And from England and from Germany, the two ideas started gaining their popularity until they met in France, where people were kind of arguing about which way is the better way to describe the calculus. Isn't this cool? Well, yes, I like that very much, but what about this other way? And the main difference between Newton and Leibniz's the calculus is the notation that they use. So when we look at the derivative or the rate of change, realistically, right, this dx that I wrote actually belongs over on this, no, over on, really? We're just going to play this game today. Really belongs over on this side. So Leibniz's notation started with this dx idea. So it was similar to what the differential was with Newton, which again most likely was a delta x. It's used most times in physics, so you see it a lot more. Hook peers over shoulder. Oh yeah. And there were some benefits in terms of Leibniz's notation. First of all, if we're talking about the same function, right, x of t, which describes the position of an object in terms of the time it's been traveling t, then the velocity of this object is going to be dx dt. And then acceleration is going to use this notation, second derivative of x with respect to t twice. All right, so one question could be, which one do you prefer?
I gotta say, I like the Leibniz notation because it tells me what's changing.
I have to agree, only because it also, for partial things, it can be useful to know whether you have a multivariable function or a single variable function.
Definitely.
Sort of a nice, convenient thing there.
Yep. So if we're talking temperature, so for instance, actually, let's back that up here. Right. If we're talking temperature and we do like T of what is the temperature at any point in this room at any time, that's going to be a 4-input function. So big T of X, Y, Z, and T. Probably I'd put it the other way around, make it T, comma, X, Y, Z, but whatever, it's fine. So what we do here is we say, well, if we want then, like, what's the differential for this? Well, this is going to be our d capital T, because we want to know the change in the temperature. And if we want to know the change in temperature over time, and only time, then we need what are called partial derivatives. So yeah, we get this d partial t over d partial little t. Should have specified. It's fine. But there are also d partial t over d partial x, right? Partial of t with respect to y, partial of t with respect to z. So we have 4 different partial derivatives that we can take where we're only going to look at specifically what is it doing in this one direction, right? In the time direction, in the x direction, in the y direction, in the z direction, and only that direction. So we acknowledge that it is a multivariable function, but then at the same time we have to say, okay, no, don't pay attention to those other things. We just want to know what the change in temperature is over this particular variable, whichever one it is we're looking at. And as Zach said, this then means that we could start looking at second derivatives of t with respect to time once and x once, or any combination thereof. And it's going to tell us exactly which derivatives we're taking. Nice. Yeah. Primes. Yep. So also then we're going to use like x prime and x double prime. And again, it's shorthand to refer to which particular function we're taking the derivative of. It doesn't actually tell you what you're taking, like which derivative you're taking, like with respect to what variable. But at this point, you should be assuming that, oh, well, this is going to be a single variable. It's just our t from before that we were talking about. There aren't going to be any other surprises. Primes really do not work with multivariate calc. You can, however, do a notation where you say, okay, we're going to do t and x here, where you put subscripts down for which derivatives you're taking, which partial derivatives you're taking. Well, that's not fair. No, it's the apostrophe that it's arguing with, because the S is out too. Yeah. So Newton really created his notation for himself. It really wasn't for other people to understand and everything like that. He figured, whatever, everybody's just going to figure it out anyway. And he was the one who really wanted to do the calculus. He didn't really care so much about other people doing it. It wasn't until, Leibniz came around where he's a teacher. He wants to make sure that everybody can understand it at like the highest level. So let's make sure that everybody can get it. And so he says, okay, we're going to be very clear about what's going on and when. Just as a note, right? Does that matter? Very open-ended question.
So the TX, does that matter?
Yep,
what I mean?
subscripts.
Yeah, so the it does matter if you're talking about things that are not continuous in particular. Usually we assume continuity, and that will allow you to swap the order just fine. But the second can was it twice differentiable functions have that, but I had to remember. So yeah, only if continuity is there can you swap the order. That's the short end of it.
Is it really commutativity though? Zach, you'd know better than I would.
It's what's this buckets theorem that says you can do that if you can swap the order of the differential if you have second order.
Right. Is it commutativity?
Yeah. So sorry. You don't exactly say commute. I've been streaming for 8 hours today, so understand.
That's perfectly fine.
Forgive me for not being on top of my game, but yeah, that's not commutativity, but you can do the
Here, I'll put it in quotes.
derivative
It
in
won't
either
matter.
order. Yeah, just that'll work. My brain is fried, so forgive me.
Yep.
And I still got a little bit of time left to go, so.
Hermitian tensor. Yes, Luciana, thank you very much. This stream will definitely be in the VODs. I will eventually. What's going to happen is like this one will end up in a separate bin that I'm just going to call like differential equations class, and then also I'm going to make a highlight of the entire stream, and that one will be permanent. So even if this is like 3 months down the road and you're like, oh wait, I need to go look at this video again, you can dig through and find it. Abuses of the Twitch system. All right, so Newton and Leibniz, right? So basically, after people in France started arguing about which one was better and why, some people had written to both Newton and Leibniz and said, you should go to the Royal Society and figure out, like, once and for all, who's getting credit for this, like who's getting which thing published and when. And Leibniz said, hey, you know what, that sounds like a good idea. And he wrote to Newton and just said, casually, just to let you know, I'm going to go to the Royal Society. Other people have pressured me because I'd like to discuss, like, who got credit for what discoveries. And Newton said, you really shouldn't do that. And Leibniz makes the, week's journey from Germany to England, makes it there, and stands in front of the Royal Society, and presiding as its president is one Isaac Newton. At which point, that is probably not a good sign. And so he sneeringly kind of lets Leibniz make his point, and Leibniz goes on to discuss that he created differential calculus, and these were the things that led up to it. And he notes that he wrote Newton but didn't really receive much of a response back, and discusses his notation, all this other stuff. And then Newton describes his particular setup, or at least gave a brief to all of the other members of the Royal Society. And they deliberate for a while, and eventually it comes to the decision, and they write a report that states that Herr Leibniz does in fact receive joint credit with Newton for the discovery of differential calculus and all of the ideas that use limits and finding derivatives and which functions get derivatives and things like that. Also solving basic differential equations, much in the same way that we talked about here, where it's just like, oh, we're gonna back up and anti-derive in order to find the other functions. The Royal Society then went on to discuss that Newton should get sole credit for his discovery of integral calculus. And this is all of the stuff that we see nowadays that looks basically like this, right? We have the integral sign, f of x dx is going to get us some capital X function plus our constant. We don't know exactly what constant it's going to be. And again, there's also the definite integrals, where we end up with f of b minus f of a when we took the integral between a and b. Okay, so Leibniz gets sole credit for this because Newton had not formalized any of it. It also turned out that throughout the rest of it, Leibniz was working at the Universität Altdorf, where he also discovered solutions to differential equations of types f of x dx is equal to g of y dy. So those that have variables which are completely separated from each other, we'll talk about that a bit later. Reduction of homogeneous equations into separable ones. So there were some yes, so all homogeneous equations could be reduced to separable equations, and was able to solve first-order linear differential equations, which we'll talk about classification in just a little bit. Newton also received credit for being able to solve differential equations of the type y dot is equal to f of x, y dot is equal to f of y, and y dot is equal to f of x comma y, so multi-variable functions like that. And also x times partial derivative of u with respect to x plus y times partial derivative of u with respect to y. This is not an equation, but I assume that this is probably supposed to be equal to 0 or something like that. So. This does seem a little incongruous compared to the others, but this is mostly because this is in partial differential equations, and so it has some interesting background to it. So anyway, Newton gets credit for this. Solving individual differential equations, not a whole lot, though. Again, he didn't formalize anything in terms of composition or symmetry. Okay, fair. Yes, so, sorry. Newton had solved individual differential equations rather than generalizing to a whole class of just differential equations. And actually, this is what we're going to see throughout a lot of what we'll talk about soon after, is that differential equations is really less about finding individual solutions and really coming up with larger, workable, I like to say, toolboxes. insert Drake meme here. Um, so I think this was kind of the point in my undergrad where things shifted for me, where I was looking at this and saying, oh, we're no longer concerned with just like doing these one-off things. This is now like this method is going to work on like all of this stuff over here, but not any of this stuff over here. Or like maybe we can pick and choose a little bit, and in order to determine which method is going to work. It is very open-ended. Differential equations has fascinated me since I first took it as a part of what was called linearity class. It was both semesters, 6 credits each. And it covered multivariate calc, differential equations, and linear algebra in 1 year. So that was some heavy stuff. Okay. I probably rambled enough. Okay, so Newton found other differential equations. So, for instance, it's named after him, so you know he knows it. Newton's law of cooling, where we had Newton's law of cooling is T prime is equal to a constant times the difference between the current temperature and the ambient temperature. Population growth and decay actually looks possibly similar depending on how you're looking at it. So there are some which are just, I don't want T. P prime is equal to K times P. Or there are instances where we have, rather than K times the size of the population, this could also have a cap to it. So it could be a constant times the current population times the difference between the current population and carrying capacity. There we go. Some high value. I think it's usually capital K, but that would just mess everything up. All right. Oi. All right, so I'll get through the rest of this kind of quickly. So Jakob and Johann Bernoulli were working at the University of Basel in Switzerland. Jakob was studying differential equations and engineering and coined the term integral. So he was the first one who came up with the word for it. The brothers were fighting constantly. Johann also did not have a professorship at the university. He was just I think that contradicted my notes. Oh well. So as I understand, Johann did not have a job at the university until Jakob died, at which point he was well respected within the community that everybody was like, well, obviously he's the spiritual successor to his brother, and also he's a fine mathematician in his own right. So he was able to do all that. Why the word integral? Yes, actually. So I assume, I have not actually looked this up, but let's actually use the line tool. You have some function, and you want to find its area under the curve between A and B, and we've broken this thing up into, wow, okay. Well, dx doesn't need to be the same, so whatever. Or delta x. We've broken this up into n parts, and then when we find the sum at the end of it, we end up taking all of the individual rectangles and we integrate them together. So bringing it together as integrate. Oh, there we go. Stack Exchange has the actual answer. That's fair. Make whole from parts. Yep. That's where I was going with it, but... Okay. And both of the brothers Bernoulli were well known for their tempers and argumentative nature, both with each other and with their students. So they were fun. But at the same time, if you studied under the Bernoullis, they were pretty much the best. So you know you got a good education, even if it was like the absolute hardest way to do it. So they especially made large strides in expanding the entire knowledge base of differential equations. There was so much to do at the time. Like, they just kept pushing frontiers further and further. So Jakob died, Johann took over the professorship, and Johann taught his son, Daniel Bernoulli. Many of you may know Daniel from the famous Bernoulli principle, which is the thing that governs the ability of wings to fly, or rather, any I mean, it's really could just be a wing, but any shape that builds pressure on one side and creates a pressure differential. Daniel did this in the river with a bunch of different shapes. So he would take different blocks of wood and put them in the river and just observe what it did. Oftentimes what he'd see is that something that was put in that, like, again, created a differential in the amount of water that was going to one side or the other, it would create an eddy on this low pressure side. And so in water, you could actually see the water depress down. There is no longer as much water in there as there is on the other side, or just in slack water, or not slack water, in the normal river. On the other side, however, you'd have this area of high pressure. The water would start stacking up. And in terms of what that does for us, in terms of flight, this wing will then have a force imparted on it in order to fill the void. So a low pressure front causes the wing to get sucked up into that low pressure front with a certain force that's called lift, and then the lifting force, if it's large enough, will cause the wing to fly in the fluid. Right, and this is, again, the start of the field of fluid dynamics. At least, you know, the formalized, super serious version of fluid dynamics. I can't remember where to go. I highlighted the brachistochrome problem earlier, and I completely did not. Can somebody look that up for me? Who was it who actually solved it? It was one of the Bernoullis. One of Johann's other students, in addition to Daniel, his own son, was Leonhard Euler, the famous mathematician who discovered the value for E, 2.718281828459045, etc., and discovered the relationship that we know. We'll just fill this space over here. It's fine. E to the I, well, okay, theta. E to the I theta, which of course Zach has used for his username, is the cosine of theta plus I times the sine of theta. This also crops up later on in differential equations a lot, so we'll be dealing with that in, well, technically I guess it's our third unit. So it's slightly different. Phobos, when did you drop? I don't know. Your evil twin. Johann posed the question. Okay. That's weird. I thought it was older than that. Okay. So Euler also proved the exactness condition for some differential equations we're going to talk about in a little bit. Created several methods to approximate solutions to integrals in differential equations. Anybody who's done Calc 2, that's where all of the numerical approximation comes from. We've got some other solutions to differential equations. We'll see Euler's method as we get into it. And during the last 17 years of his life, he went blind and then dictated all of his research to his students. And then, naturally, they had some discourse and bounced ideas off each other. Slightly like an old world version of Stephen Hawking. He did have verbal faculties still and could get around just fine, but he was blind, so needed at least some help there. Feel like we're talking in circles? Yep. Oh, Don. No, hang on. Where's the thing? All right, Euler then went on to also make contributions to partial differential equations, multivariate calculus, series solutions to differential equations, and a whole lot more. So he did ridiculous amounts of work, and that's just in differential equations. All of us also know, some other place that he did a significant amount of work, and it's just ridiculous. One of the other big contributions was that Euler formalized all of our notation. I keep telling my students, pretty much, not literally, but pretty much every piece of notation that you see in mathematics, you can thank/curse Euler for that one. So, okay. So then we've got couple more people to just highlight. After the Bernoullis, the scientific progress kind of went a little bit to the west into France, and most of the major contributions in the 1700s were mid to late 1700s were from French mathematicians. We have Pierre Simon de Laplace, who lived in Normandy until he went to Paris. He figured out the Laplace transform, which we'll talk about later on in the course. And Oliver Heaviside was the first person who connected it to differential equations in about 1880, so close to 100 years after the discovery of the Laplace transform. Why is Euler everywhere? Because he was that much of a genius. Again, Heaviside was the one who connected it to differential equations and said, this could be useful. Joseph Louis Lagrange succeeded Euler as the chair of mathematics in the Berlin Academy. So he was a French mathematician, although he went to Germany for his work, and was able to find the general solution of an nth order linear homogeneous differential equation. Again, we'll talk about what that means. And some special parts of that, which we'll come back to later. He was also heavily involved in partial differential equations and multivariate calculus, just like Euler, his predecessor. Pretty much. Okay. Yeah. We'll go to the right here. So the next thing that I want to bring up. If anybody who's around, and particularly Stucky and Zach, you're in the channel here, so come up with a few different types of differential equations you've seen before, and how are they different and same from each other? So, Waffle Walrus, Euclid was not really involved in differential equations. So, he definitely helped out with a lot of the geometry and the foundation of trigonometry, all sorts of cool stuff like that. Phobos, thank you. Anybody else can come up with some too, yeah?
I would throw in the, let's see here, the logistic equation.
Which one's that, do you know? Offhand.
So you can do what? Let's see. It's 1 over. So you have a constant times. So let's make this dy dt equals a constant times y times 1 minus y over another constant. So pick your favorite letters there.
Times. Sorry, this was what?
1 minus y over some constant. That's a fun one. It's called the logistic equation. I think we could put in the, let's put in the heat equation. So you can do, let's see, partial u partial t equals minus a constant times partial, the second partial of u partial x. It is the best one, Don. I have to agree. I have to throw that in there. It's called the heat equation. And you want to do the squared on the partial x.
I am nothing if not literal.
This is another as a personal thing. I prefer not to write uxx, although that is we should, if we're going to be complete about this, it should be noted that ut equals minus k uxx is commonly written, so you'd want to be familiar with at least what that looks like. My personal preferences aside.
Yep, fair. So like we discussed earlier, having the partial derivatives as subscripts is an option, and that was something that Leibniz championed, but Yeah, Zach, one more time. What was it about it?
It's just the nature of the variable, not knowing how many variables the function is of, right? Like if I see partial u partial t, I look at that and say, well, u is a multivariable function. So that helps just with notational things. I've run into trouble if we're not careful with that.
Dr.
That's
Gold.
another.
Sorry.
No, that's I was gonna say the predator prey one's good.
Yep. Oh. Rating party! Hey, Ren. Good evening and welcome. This is our differential equations class. My name is Obi-Wan Pez, and this is N Simplex Pachinko. Hope you had a good stream. What did you get up to? Currently discussing different types of differential equations that you might have seen before. If anybody has any differential equations they'd like to drop in chat, feel free. Stooky. Raider from Ren. I also do that. Yeah, so Dr. Gold, what is the predator-prey model? Yeah, sorry everybody, story time took up way too much time, so... Volterra equations? Yep, okay.
You could I think you can do like your x prime equals the constant. You can factor out an x. So factor an x.
Oh, yep.
And then constant minus different constant y. I think that's what you want. Yeah, I get that. Dr. Gold. Makes sense.
Ooh.
And then you do the same thing, but with y and a negative constant first.
Or we could do... This is completely... You're gonna hate me for this, but whatever.
Yeah. Well, that's fine. That's fine. It works.
They're backwards. Yeah. So anyway, this is a fun one. I actually did some work on this in my nonlinear differential equations class. I think it was. Again, we'll do classification later, but yeah, the main point of this is like anytime you see x's and y's together in the same equation, this is their like interaction with each other, and what does that do to each of these things? So in the case of prey, nope. I guess prey is x in this case, because xy is on the beta, which is a negative term. So that's going to end up... Yes, there it is. I should read the page that I opened. X is the population density for the prey, and variable y is population density for some predator. So yeah. Their interactions will be destructive to x because that term is negative, and constructive or reinforced to y because that term is positive. Alrighty. Alright, so how are these similar or different from each other? Okay. By link, Dr. Gold, what do you mean? Or if either of Zach or Stuckey, if you want to explain any of this as you see it, you can jump in anytime.
Yeah, we've got partial differentials with the heat equation.
Whereas the rest of them?
Just a single independent variable. Looks like.
What do we call that?
What do we call that? It's a derivative.
A single what? A single.
What kind of derivative?
You have a partial derivative and an ordinary derivative, right?
Yeah.
Those are the two.
I don't actually know if this is the correct word, but whatever, it's fun. So...
The partiality. I was gonna say I don't think that's standard, but I'll go with it. I love it.
So we could have the partiality or ordinarity.
I think Phobos would say. I think what Phobos is saying about total derivatives is fine. That's a good way to say it.
That's ordinary.
Yeah.
Right, so what's the status of our particular derivative? Is it partial or total? Is it ordinary or partial? We have orders of derivatives is going to be something that we're going to focus on. Anders?
So all of these equations are like, you don't see the independent variables except in like except like in the Leibniz notation, right?
Right. So actually, yeah, all of the ones that you highlighted, yeah, even this one here, all of the ones you highlighted actually belong to a particular class of variables which isn't part of the classification that we do usually at the beginning. It just kind of comes along when it comes along. But these are called autonomous. Where derivatives are v. If we're talking about time specifically, we could call this time independent. So no matter when you start the relationship or start looking at this particular relationship, the derivative is always going to be the same at that particular xy value, or sorry, at that particular y value, at that particular u value, whatever we've got in here. Or not independent, sorry, invariant. So these are all time invariant. So doesn't actually matter when you start. It's just a matter of if you reach the same values, you end up with the same derivative values as well. So like I said, this isn't actually one that we typically will talk about in terms of like classification, but it is kind of important. It is a different type of differential equation. That was one of our Newton ones that we saw earlier, was the solution of, I need to organize this better. There we go. Newton's versions, right? He was able to find y prime equals f of x, or as we saw them, y prime equals f of y. So some function of y, the dependent variable. So that's what we see for all of these. They're all functions of only the dependent variable. Right, and Dr. Gold brings up homogeneity. What is homogeneity? Okay. So homogeneity is a particular differential equation, or a, a differential equation will be said to be homogeneous when that particular differential equation has no term that is a function of the independent variable alone. So if we end up with, I don't know, somebody want to give an example?
Well, actually, the some of them up there are already homogeneous, like the y equals y prime, for example. If you rewrite it, you could write it so that there's a there. That I mean, that would do it. We usually think about the equals zero thing, like Dr. Gold says, but y prime equals y would be fine to
Yep, so in this
use.
particular case, right, we could just shift this over to the other side and then end up with y prime minus y equals 0. And that's the shorthand, is really, like, when we get into this, we want some sort of function of our eh. mm. Yeah, I have to be careful of how I say this. Um, isn't y of x a function of the independent variable? So, in theory, yes, but it's not a function of the independent variable alone, because it is still like its own variable. So what we really mean is there going to be some function on our left-hand side if we can organize everything, right? So all the stuff that contains any amount of y's whatsoever. This is going to be a function of y, y prime, y double prime, and etc. And maybe also using t, but like as a multiplier. It's never going to be an additive term. I don't know how to say that properly. So we can have a time term, but it has to be multiplicative. Whereas on the other side, we have some g of t, which is of t only. So I don't care how complicated it is. It could be extremely complicated. If it is a function of t alone, then if, right, g of t is not equal to 0, then this differential equation is non-homogeneous. Oh dear. We're getting to the point where we're skipping. Sometimes called inhomogeneous. But for some reason, heterogeneous, like I've only seen this in a rare number of cases. I don't think I typically see it. So in this particular case, this one right here, since it is all stuff that contains y's on the left, and then equals 0 on the right, i.e. there is no term anywhere, which could be written as g of t alone, which is not equal to 0, then this particular differential equation, and as Zach pointed out, all of the rest of them that we wrote in the previous section, are all going to be homogeneous. Would y prime minus ty equals 0 be homogeneous? Yes. So that was my point with the multiplicative t thing that I wrote up there. So yeah, y prime minus t times y equals 0 is also homogeneous. Yep. So a lot of times if we want to generalize it and like seriously generalize it, we'll say something to the effect of like, p1 of t times, this is a terrible idea. Hang on. P0 times y plus p1 of t times y prime plus ... plus p n of t times y nth derivative is equal to, again, g of t over there. I don't want to get too far into the weeds. We're going to definitely talk about this more later. It really crops up a lot when we're starting to deal with second-order differential equations, which is going to be in the third section of the class. So once we get past the first-order derivatives and we talk a little bit about linear algebra, then we're going to get into our second-order derivatives, and that's really where homogeneous and non-homogeneous equations shine. Okay. Anybody have any questions? Lily Cubed and Dr. Gold, thank you for the follows. Okay. As we discussed, or as was brought up here, there are constants in all of these. Up here we have a -1, and here we have a +1, so they exist. And oftentimes we're using, K, C, whatever we have, alpha, beta, gamma, and delta in terms of our predator-prey equation. Yes, there are going to be constants all over the place. In the classification sense, we're not going to distinguish between the types, like whether or not they have constants. That's just going to be something that exists. Good exercises, of course, are going to be what happens if you change the constants and see what happens, and does that change the nature of the solutions, or does it always stay the same? So we'll take this one up here. All right, and there is one other type of classification, and I have actually said the word now that I think about it.
How about linearity?
Linearity. Oops.
Yeah, some are, some aren't.
All right, if a differential equation is linear, then it is linear in, this is very strange, but it's dependent variable and all of its derivatives. Now, that's a little weird, and I come up with all sorts of just messed up versions of this every semester. But let me tell you, this one right here is a linear differential equation, no matter what functions p we have. or g, for that matter. It does not matter. Every single one of them could be something completely different. It doesn't have to be a polynomial either. That wasn't implied by my p there. So we could have natural logs, we could have exponentials, we could have polynomials, we could have roots and inverse. Yeah. The 1 over. Yeah. Function. Thank you. Right? We could have literally any functions we want in for p and in for g, which are in terms of t only, and this would still be a linear differential equation. Because what we care about is what's happening with y and all of its derivatives. How would I go about making this nonlinear?
So the key thing here is that you can make this a this p0 y and so on. You can make that a linear operator, and then you turn it into basically an ax equals b as you would in linear algebra, or in this case ly equals b, right? So to make this nonlinear, what you'd do is you'd maybe have a y squared term that shows up, or multiply the y prime term by y. So something like y plus y prime equals 0 would be, yeah, something like that.
And what was your second example?
Y plus y prime equals 0.
Yep. So if we had a y times y prime, right?
Yeah.
This is also going to be nonlinear. Yep. E to the y double. Oh.
That's really my evil cousin here.
That's really gross. Right. So all of this stuff would be
right there. E to the y prime.
all this stuff would end
y
up being
double prime.
nonlinear. Yeah. And the thing is, right, any one of these being changed anywhere in the differential equation is going to make the entire thing nonlinear. So even if it was just one of them, these are just multiple examples within the exact same problem. I mean, not that we want to do this, because gross. E to the 2 prime y, yep. Okay. Anybody have any questions? Anybody have any clarifications? Anything that maybe I didn't bring up that you want to bring up, or weird edge cases? Is it homogeneous, though? Well, you tell me. How do we make it homogeneous? Okay, so to make it homogeneous, we said earlier, all that we care about is that the other side needs to have a g of t, which is equivalent to 0. So anything you want to put over here is either going to be 0, or it's going to be a function of y, y prime, y double prime, etc. For simplicity's sake, usually we say, okay, we're just going to simplify this to 0 and say that all of our y terms got shifted over to the other side. Right? All the terms that contain y, just shift them over to the left-hand side and leave the right-hand side for any term that is just a function of t. All right. Other questions? So we didn't really talk about orders of derivatives, but right, what is order?
So you could think of it maybe as the number of derivatives, so y double prime being a second order derivative because you're taking two derivatives of y, for instance. You could make the 42nd derivative if you wanted to, or
Always 42.
it's always 42. That's the important one, right?
Oh, I put our laundry away. I would have had a towel like right off screen, but maybe that's too much of a flex. Although, almost as good. Oh no. Oh no. Yep, looks like my Hitchhiker's Guide is also currently in a pile somewhere. I would have thought it would have been to hand, but oh well. And in this case, we're going to talk about in terms of an individual term. It's going to be whatever's the highest number of derivatives taken. So if we come across a single term that, again, if it was in our big example over here, we've got y, y prime, y double prime, all the way up to y nth prime. Whatever that value for n is, that's the highest one that's going to exist here. And so we're just going to say, once it's all organized, we say, what's the highest number of derivatives that we have? This one here, whereas gross, does still count. So this is going to be a second order differential equation. It's going to be nonlinear as discussed. If it has no g of t term, g of t is only equal to 0. And so therefore, this will be homogeneous, and we are only using ordinary derivatives. So this is our this is going to be our classification for this particular one. And let me actually write it out. So this is going to be ordinary. Second order. Nonlinear. Homogeneous. Differential equation. And in terms of like the order in which you put these, it really doesn't matter, but at the same time, like it's that weird thing where like you kind of intuitively know what order to put the if you're a native English speaker, right, you intuitively kind of know what order in which to put the adjectives. So in this particular case, the way that it just sounds best is kind of it's ordinary, second order, nonlinear, homogeneous. That's just you after like years of experimentation. Okay, let's do further right. Oh. I thought I was going to classify these. All right, whatever. It's not the wrong picture, I know that much. So let's talk about the first one, I guess, real quick. We have the differential equation, y prime equals 7y. So what is going to be the classification for that one?
So that's your, what is it? We got a first order, linear, ordinary. What's our other one? We got to remember the four here. So you've got first order, linear, ordinary, and I'm trying to remember what your criteria here are.
Homogeneity.
Homogeneity. Oh yeah, it's homogeneous. We got that.
Right, but it's not equal to 0.
Right, but it's a function. I mean, like separable things are, by their nature, homogeneous. Right.
We don't know the definition of separable. Anyway.
Sorry, I forget. I forget what I don't know. Right, I'm not supposed to know that.
But yeah, totally.
I mean, I know what a partial derivative is coming in, right? I don't know the definition of separable, so I'll be quiet.
Yep. So ordinary. First order. Linear. Homogeneous. Okay. So then the next task on A is verify that the following equation is a solution for the given differential equation. So for A, this one's going to be pretty easy. How do we do that?
Take derivatives. And that's the left-hand side.
Go for it.
Oh, derivative here is what, 35 e to the 17.
And we're going to presume here. So Anders, that is my claim, right? Is that all of the things on the left are going to be solutions to all of the things on the right, the differential equations on the right. So again, that is my claim.
And then take 7 times what we got here, which looks like 5 e to the 7t plus 49. I dispute your claim.
Right. So in this particular case, yeah, oh no. I used an example that was not true in order to highlight, right? It's really close. But in this particular case, we're off by a constant, which does significantly matter, right? This is going to be a function that has been shifted 49 in one direction. So its asymptote and all of its features are going to be vertically displaced. So that does not work for this one. All right. And I think most of the rest of them should work. But I think maybe Zach, you want to do one. Stucky, you want to do a second. And then I'll do whatever's remaining.
Sure. Only half of that. Oh, did we lose Zach?
Oh.
I think we lost Zach.
Is he sitting in? No, okay. I was worried he was sitting in the audience section.
Yeah.
All right, so which one do you
Yeah.
want to do?
C. Do I want to do C? Sure.
Yeah, no worries, Anders. Go for it. That's what we're here for. So the solutions are supposed to be functions, asterisk, right? What we're really looking at is like, is it a function of whatever input variables we have? So if it's a multifunction, in terms of like the temperature one that I talked about earlier, right? It's capital T of X, Y, Z, and lowercase t. So a position and time. So for any combination of X, Y, Z, and time, there is one output. So in theory, this will, again, do the same thing, is that like y being 5e to the 7t is going to be a function. Y equals this one here, it's exponential again. This one here, m, the one that Stucky's doing, is in fact a function, right? It is, well, we'll talk about this in a little bit, but Yo Tizzle, thank you for following. But yeah, let me know what your thought is on that one. I'm going to do D, because I'm a glutton for punishment. All right, so we've got P of X. Stucky, I'm just going to talk, so apologies. P of X is going to be 4X plus 8. We notice that in the rest of the equation, we have a dp dx, and we also have a, ordinary, second derivative of P with respect to X. And so when we look at this, we want to then take both of the derivatives and say, okay, we know how to take derivatives. The derivative of 4x plus 8 is just going to be 4. And then the second derivative of 4x plus 8, or the derivative of 4, is just going to be 0. Okay, so then when we do that, we notice that in the differential equation, we get x squared times second derivative of p is 0. So that term's pretty nice there. Plus x times the first derivative of p with respect to x is 4. Plus, this is x squared minus a quarter. All times the original p, which is 4x plus 8, is equal to, right? Yeah, is equal to 4x cubed plus 8x squared. This is going to be a little bit long over here, but it's all right. Plus 3x minus 2. Not sure if there's a meaningful difference when we see the solutions as functions as opposed to seeing them as equations. So the solutions to your differential equations are going to be whatever your dependent variable is, and it should eventually, if there is a solution and you can find it analytically, which is what we're going to concentrate on, then you should be able to get it as a function of your independent variable. Again, it might have discontinuities, right? So as you're saying, is it a domain thing? Maybe, but that doesn't stop it from being a function. Like even if it has multiple discontinuities, it's just that it doesn't exist at those individual locations or intervals. Okay, This is going to be 4x, and then plus. We now need to multiply all this stuff out, so 4x cubed plus 8x squared minus a quarter times 4 is going to be 1x, and negative a quarter times 8 is going to be negative 2, is equal to 4x cubed plus 8x squared plus 3x minus 2. And again, if you can see this bit here, you notice that we do in fact have the exact same thing. So I usually write it out explicitly just so it's clear that, yeah, in fact, this is literally the same thing. Pardon me. Okay, so D is telling us that here, this is in fact the solution to the differential equation. 4x plus 8 is a solution to x squared second derivative of p plus x times first derivative of p plus x squared minus a fourth times p equal to that polynomial. All right, Stucky.
Hey,
What'd you get?
what'd I get? I got good news. We took a derivative, and that turns m into negative 4/100 t to the minus fifth plus 5/9 t to the fourth. And so when we multiply the original by 4/t, the t to the minus fifth term cancels out, and the t to the fourth term conveniently lines up. 5/9 plus 4/9 is equal to 9/9. So that's exactly what we want on the right-hand side of the equation.
Cool. And again, anybody who is not like super strong in their calculus, in this particular case, we're just using power rule. So take down the exponent we have and subtract 1 from it. So that's why we get our negative 4/100 t to the negative fifth, and likewise 5/9 t to the fourth. And as Stucky said, we take the next, take the original and multiply it by 4/t, and we get very nicely, very conveniently, everything knocks out exactly the way we want it, and we get t to the fourth on both sides. Woo! All right, B, I'm going to just skip for now, but again, same deal with this one. We're going to take second derivative and first derivative and the original function, plug those into the appropriate locations, and in the end, this is going to end up equaling 0. Okay, so what do you all notice about the proposed solutions compared with their differential equations? Oops, Zach's back.
Hello.
It's one of the problems with not having it on that part of the screen the whole time. Hey, Zach.
Hey there, I'm on my phone right now, so.
All right, sorry about that.
My Wi-Fi is sort of dead. I'm waiting for it to restart, but I'm on my phone, so I'm still listening.
Well, thank you very much. If you need to conserve your data, feel free.
We're fine.
Okay, so what do you all notice about the proposed solutions compared with their differential equations? Now I have to remind myself what the answer is. I honestly can't remember what it was that I was going for with that one part, but apologies.
So I noticed that all of the differential equations are or not algebraic, but are rational. Um, and that's not true for the solutions. Um,
Okay, so like the way in which they're
although-
related to, um, the way in which they're related to each other, right? Or to themselves technically, right? So the derivative is related to the original function, has been through what appears to be rational function sort of setup.
right.
I like it. Does it have to do with derivatives? I don't. Sorry, Yotizel. I don't know if that was actually in reference to this question, so apologies. Um, I think maybe I was going for classification here. Let's assume I was. So in terms of classification, is there something that is kind of a through line for all of these?
No. That's my answer.
Could be fair. Reference to E. Yeah, okay. So I'm going to say that it is to do with the classification. And we'll go with that. I'm pretty sure that's right. So in terms of the orders, or well, okay, let's go even further back, right? In the order in which I put it down. Right, what kinds of derivatives are we taking?
We do have all ordinary derivatives.
Okay, so these are all ordinary. We didn't do any partials. And then, yep, order.
Small.
Specifically?
First or second?
Either first or second derivative, yeah. So all of these end up being order 1 or order 2, depending on which prime and double prime is going to be the highest. Yeah, okay. And then third, I did linearity.
Are these all linear? Yeah. Yeah, I think so.
Because?
Because I mean, yeah, they're what's the definition? They're linear with respect to the dependent variable.
And then all of its derivatives as well, yeah. So we're looking at first one here, y prime, and then 7y. There are no products of any of the y terms with either itself, meaning, you know, y squared, y to the third, etc., or with any of its derivatives. And likewise, not the derivatives with any of the other derivatives. If you end up seeing those things multiplied together, that's a problem. So here we see that our y's are separate from each other. They have their own terms. They're not mixed at all in terms of the dependent variable and its derivatives. And again, second one, we have constants that are all multiplied by the different derivatives and y. Third one, we do have 4 over t, but again, this is still linear in m, being the dependent variable. So dm dt is just by itself, and then 4 over t times m. This is still linear in m. And then likewise on the next one, this is the one that kind of trips some people up mostly, I think. You know, the rational one maybe, but x squared is also something that trips people up if they see a polynomial ahead of time. No, this can't possibly be linear. It's a polynomial, right? It's a quadratic. But this is the thing, again, it's p double prime is not multiplied by any other p term. It's just p double prime times some function of x, which is the independent variable. So we're okay with that. So all these end up being linear differential equations. And lastly, homogeneity.
Mixed results.
Right?
A and B are, C and D are not.
Right, so A and B have homogeneity because they have no, in those cases, function of t by itself. And then in C and D, C has a function of t by itself in t to the fourth, and D has a function of x by itself in this polynomial. And that also includes constants at the end. So in fact, if this was none of these other x terms, but then it just equaled -2, that's still a function of x, which is not 0. So that could be also something that throws people off. But any questions? And yo tizzle, right on the nose. Good job. Other questions from chat or from speakers? Well, what is the solution, right? So what we're going to see is in the next class, what we're going to do is actually find start finding some of these solutions analytically, and then be able to say, well, this isn't the only solution to this particular thing. Now, you all know that there is one particular way in which antiderivatives or taking integrals, indefinite integrals, ends up showing us multiple possible solutions. What's that? Yeah, using Wolfram. All right, touche.
The question is, yeah, so what is the question?
How do we compare what we have here to the solutions? So I was saying when we were taking integrals in Calc 1, we always ended up with what? Like we were saying, there are many multiple solutions. And when we took integrals, that always showed up how?
Yes, plus C.
Right, so that constant shift that we don't know what number it's going to be. It's just the general solution is that we include this plus C at the end. So in terms of, let's not do A because it was wrong. If we just drop the plus 7, this would have been a possible solution to this differential equation. And in fact, it is the only possible solution to that differential equation. Sorry. Brain go burr. Um, okay, that was not a true statement. Sorry. If it was just 5e to the 7t, there is a way in which we could get multiple solutions, and that is by changing the 5 out front. So if we had ignored the plus 7, and we had had a different multiplier out front, that also is a solution to that particular differential equation. So that kind of answers F. No, that also answers G for us a little bit, at least for A. So yeah, being off by constants somewhere in the equation is going to be probably our solution in terms of like what other possible solutions are there. It just kind of depends on the type of differential equation, and we'll talk more about those as the class goes on. Would any of you been able to find solutions without me stating, here's a solution, verify it? Or would any of these types have been obvious to be like, I know what the solution to that is?
I feel like maybe it could have fudged A. The others feel a little trickier.
Yeah, I mean, A is pretty obvious in terms of like, oh, the derivative is a constant multiple times the original function. Yeah, I think I got this. Right? The second one, maybe you could say, okay, if the derivative and the second derivative have to be of the same type, then maybe it's an exponential function. And that is one way to get into it. The constant, again, would have been harder to figure out because it would probably take some guess and check to determine what exactly it was. And then, yeah, the C and D, I would not expect somebody to just be able to like pull together an answer and just be like, here it is. These are going to take a little bit of extra time and effort to like really nail it down and figure out what the proper answer is going to be. All right, and then G, do you think you'd be able to find any other solutions for ones above? Again, we talked about A. What if we just change the multiple out front? Well, ignoring the plus 7 on the end, which broke it. Changing the 5 to like a 12 or a negative 7 would have been perfectly fine. Or I guess I could say, are there any of these which you think there are alternate solutions?
Yeah.
Any inkling as to which? You know?
I think for all of them. I'd
All
be
of them.
happy to say.
Okay.
Yeah.
So I will say one of the things about this is that there are potentially more solutions of different function types depending on the differential equation. So some of them will have different solutions. It's just that maybe I have no idea what it could be. I have seen one that has a like, you know, an exponential type function as a solution, but also it has a like a simple polynomial as the possible solutions. So that is an option. Most of the time when we go through this, there is going to be like a solution, and that is going to be it. I will also say that B has an interesting result, and we're going to get into that when we start looking at it in, again, second order differential equations, so like unit 3. And H, what other famous math problem echoes this scheme? basically, what I'm trying to do here is compare what we were doing in A through D with the question F. Not Newton's law.
I'm going to take a stab. What you had in mind was maybe P versus NP?
Yes. So coming up with a particular verification that this particular equation is or is not a solution to the following differential equation is a p-complete problem. It's super easy to figure out. And I hope I'm using this correctly, so smack me if I'm not. So this is going to be a p-complete problem. It's super easy to verify whether or not a particular differential equation has this given solution. It is not always super easy to figure out what said solution is going to be. And in fact, in some cases, differential equations are going to be impossible to solve, or at least impossible to solve analytically. There are going to be some examples that we throw out here and there, which will require the use of numerical analysis in order to determine what the solution is going to be. In some cases, those are going to be just wild approximations. And in other cases, toward the end of the course, we're going to talk about series solutions, which technically are 100% precise if you go out to infinity. But they're not necessarily the easiest things to do, nor is it an analytical solution in terms of like, here's a function that's going to be simple and tell you what the solution is going to be. So there are going to be some that's just like, well, we can't come up with a nice function, so we're just going to use a series and say, well, it's infinitely long, but hey, it's all right. And this echoes, yes, Phobos, this echoes the problem that we have in Calc 2, where pretty much any function you throw out, you can derive it super easy, or at least somewhat easy. But then if you try to integrate said function, there are some where it's going to be hard, if not impossible. And actually, right, one of them can tie into Penn Center's class. So e to the x squared dx is going to be not solvable in a standard analytical method through Calc 2. What you're going to have to do is use complex analysis in order to get this to a nice place, in order to figure out what the integral of this particular function is going to be. So gets to be just all sorts of awesome. So going to put in a plug for, thank you, Fembox. Going to put in a plug for Penn Center. We are currently in his Discord server poaching resources. And also, Penn Center is doing a complex variables class, which will run tomorrow, right? I think that's what we got.
Yeah, that sounds right to me.
If you go over to the Discord server on the left-hand side and select the class complex variables, yep, that's all in there. And yeah, 6 to 8 p.m. Pacific time, so I will not be awake for that, but I will definitely catch the videos on demand. So I would like to thank Zach and Stuckey for coming on here. And if anyone else is interested in coming on and being part of the class for future streams, please let me know. DM me or find me in Discord. Post it in the class section for differential equations, and I'll respond to that as soon as I see it. And I don't know if anybody else has any other final thoughts. I do have like 2 more questions on this. We'll push it to next class.
All right.
Thanks so much for hosting this, Obi.
Yeah. Thank you for coming, and we'll see you all in the next one. We are going to raid over to Merriweather, who is doing some microprocessor programming. So we will see you all next. Oh, channel's offline.
Oh yeah, I'm also seeing him off. But it looks like Gold is up.
Dr. Gold. Oh, I have too many people in here. Yes, okay. So we're going to start the raid over to Dr. Gold. Going to give about 10 seconds, and we'll send everybody over. So thank you very much, everybody. And Yotizzle, yes, I will take the questions for differential equations. And if you come see me in, oh no, he's watching. If you come see me in the Discord server, I will send that over. So thanks very much, everybody. This is Obi-Wan Pez for N-Simplex Pachinko. And we're off. All right.
And we're off.
Thanks, everybody.
Yeah, thank you.
How'd you think it went?